So hello everyone and welcome to our webinar finally on tackling silica dust health and safety challenges. I'm Peter Shields and on behalf of AirMet Scientific, I'm thrilled to introduce you to today's guest speaker, Dr Winnie Chu, founder, president and CTO of Nanozen. We understand the critical importance of workplace safety and the presence of respirable crystalline silica dust presents a substantial concern across a wide range of industries. With Dr. Chu's wealth of knowledge on the subject, we will explore silica dust-related health and safety industry challenges and gain a deeper understanding of the difficulties of distinguishing RCS particles in the air. So I'm excited to learn from Winnie, and I hope you are too. So without further ado, I'd now like to hand this over to you, Winnie.
Thank you very much, Peter. Good. Hello, everyone. I'm Winnie Chu. I'm the founder and CTO of Nanozen. So I'm a chemist by training. I taught industrial hygiene at the University of British Columbia for a number of years. So my research is semiconductor sensor, but I also develop analytical method in the lab for different chemical hazards. So it's just when I was teaching the students the pump and filter method and interacting with government agencies and the industry, I realized that we need to have an alternative to the pump and filter method, waiting for the result to come back. I'm pretty sure a lot of you share the same feeling as me, that by the time the filter result came back, even if workers were overexposed, they don't remember what happened a few weeks, a month ago. So a lot of them that I interact with are immune to, so I failed. What can I do? That's unfortunate. So took me a few years. I really wanted to change the status quo, and that's where we are. And thank you again for joining me. So I'm going to focus today on one specific topic, which is silica. Do we need a real-time silica detection? So this couple of years in California, Dr. Fazio, who is a pulmonary critical care physician at the Oliver View UCLA Medical Center, but she was really shocked and being alarmed by the number of cases with young men in the construction industry that have silicosis, and people as young as 20s and 30s died from it because of the lung failure without any other alternative to help them. And this work, it was just published in JMA Internal Medicine. So in the industry, silica is naturally occurring. And so exposure to respirable crystalline silica can cause cancer, silicosis, and other things. And so in stone cutting, metal production, and including the water filtration and treatment plants, they all want, if you aerosolize or disturb this silica, operators or even the community people could inhale these crystalline particles and have potential to develop into cancer or silicosis. So I call it a revolution. Only about 10 years ago, 94, 95, OSHA lists silica as a priority for rulemaking. 96, the World Health Organization, International Agency on Cancer Research, IARC, first classified silica as a known human carcinogen. 2016, OSHA finally announced the final ruling to protect workers from exposure to respirable crystalline silica. It's less than 10 years ago. And pretty happy to see that in Australia, there's a recommendation for the national ban on the engineering stone because there's no level of cancer-causing silica is safe. So in Canada, the average is about 400,000 Canadian workers that are exposed to silica at work. So it's interesting. We actually export about 376,000 tons of silica sands and quartz. and then import about 5 million tons of silica sands and quartz. And so there are a lot around us. So the occupational exposure limit, OEL, in Canadian jurisdictions ranging from here in British Columbia 0.025 milligram per meter cube for 8 hours to 0.1 milligram per meter cube in Quebec for respirable crystalline silica, quartz, and tripline. So environmental exposure is set differently. So in Ontario, it's 0.005 milligram. Respirable crystalline silica in 24 hours. So I think a lot of us have done and are familiar with the occupational health sampling. Currently, regulatory approved sampling method from the 60s is using a cyclone and to follow the standard respirable curve to collect respirable fraction of silica onto a filter and then wait for the filter result to come back. It's very important and critical work. The challenge is the waiting for the result and to come back and the shipping. And in a lot of places, the reliability of the shipping the filters to the lab. And so I set out to try to pinpoint silica exposure source. We have been working, and then our real-time monitor can actually match with the NIOSH Evade software, so you can pinpoint where the peaks happen and hopefully find out what happened and eliminate the source. Again, I think a lot of us who do industrial hygiene and occupational health sampling are familiar with two types of particle counters out there. One is similar to ours, is optical particle counter. It counts every single particle and size them. So we also call them aerosol spectrometer, and another one is snifflometer. So when the laser light sees a passing sampling air with particles, you reflect, scatter the light, and there's usually a defined range of scatter angle. We will let this signal pass through to the detector. And so good thing about optical particle counter is it counts every single particle and size them. So accurate OPC should be able to give you a good size range of particles, and such as respirable fraction of silicate in the air. However, the scatter depends on particle size and refractive index, which is usually unknown in the field. So you can't size particles, but you'll be challenging to understand the type and the composition of that particular particle. So I'm going to switch gear, just talk a little bit about the basic principle of light, or a reminder of some of you are familiar with light. So light, such as sunlight, is naturally unpolarized. So light is actually an electromagnetic wave. So if it's natural unpolarized, the electric field would oscillate randomly along the propagation. And so there are different types of polarizations that we can produce, or some are naturally occurring. So linear polarization, there's only just like a slit, and there's only one plane of polarization. Circular and right-hand polarization, there are two plane polarization, or the elliptical type. And so the polarization ratio is generally defined as the ratio of the two orthogonal composition. So lasers are generally linear polarized. So there's only one plane of polarization, the electric field allowed to go through to the detector. And by using different technique to polarize the light differently, one can determine the particle size. You can actually figure out the type of particles and the composition. So what we have done on the DustCount that a lot of people are using to study particle size distribution or the general mass concentration is to add the polarization to the instant laser light. So the characterization of polarization state is then affected by the material during interactions. And so by receiving angle at different part, and by receiving the ratio of different polarization, you can then calibrate the monitor beforehand to the specific material and tease out the interference, and to then use it as a silica detector. And so there are cases in the reference that they were able to also achieve what we have been doing, separate different materials, including quartz and other zeolite. Except most of the cases, there are fairly bulky instrumentations. And so it sounded pretty straightforward to just adding polarization to instant laser light, but again, it's all in the critical details. By only using polarization and with the laser light, it won't give you the accuracy of actually separating one type of particle from another. So what we have been using is also our flat top lenses. So imagine any light, including laser, naturally will be a Gaussian profile, and depending on where the particle hits the light, that determines the particle size. But as you can see, even if the same size of particle, depending on where it hits the light, will give you a different particle size. And that's not going to be accurate. And it will decrease the accuracy of the composition as well, determination. So we have then created this flat top profile. So change the Gaussian curve to a flat top profile. So then increase the chances of particle only hit on the top part. And in that way, not only you increase the accuracy of determining the particle size, you increase the accuracy of determining the composition of the material. And so we were able to use this 3-in-1 lens, like we call it, to guide laser to the flat top, which enhance the particle size distribution PSD determination. And we also use time of flight with depolarization of the laser light to decipher the 3D chemical information. As you can see, that these are the 3D image that we usually obtained behind the theme of the monitor to determine the type of particles. And so we call this spectral, our first generation particle size PSD and particle counter, and is DustCount. This generation of silica sensor, we call it Spectral Aerosol Sensor, SAS. So as you can see that we were able to achieve single silica particle identification separated from the carbon and then polystyrene particles, just by using the polarized light and determining the polarization ratio. So our Respirable sampling impactor was sent to HSC at UK for them to determine our penetration curve. And then in our lab, and same as in AirMed in Melbourne now. Now we have two setup, one in Canada, one in Australia, that we are able to calibrate particles. So people have been sending us dust particles or chemicals to calibrate into their monitors. Some are different than other, even though if it's a silica monitor. And so I encourage you to work on a project with us. And so all the monitors are going to be calibrated and validated with either FTIR, XRD, or infrared, the standard method for RCS detection. We are going to use calibrate silica, your specific respirable silica mineral, among the other minerals that potentially could interfere with your site-specific silicate. So I do want to, I'm pretty excited about we're able to pinpoint different chemical among the airborne particles in different sites. And so really welcome to have, if you are interested, a project with different sites. And both Peter and I are going to be at the AIOH in Melbourne, December 4 to 6, I believe. So if you are interested, please make an appointment with Peter, us, so we could, this is our contact info. to talk about what would you like to do next. Can we help to put a project together and help you to determine your site-specific silica and just to help improve the overall silica exposure situation.
Thanks, Winnie. If anyone has any questions, just type them into the chat and I'll ask Winnie to answer them. So I've got a question from Ben saying, how does the Nanozen pump cope with very high concentrations?
We have done some work with other sites. So if the concentration are higher than what we can handle, there are ways of adding an impactor outside the monitor to impacting out preferably anything larger than 10 micrometer that we don't care. So we have done that, but you need to add another impactor.
Okay, and we've got a question. Can you measure silica and silicates separately?
Oh, I believe so. Yeah, so they are in our graph. I cannot say it's 100% separate, but there's some overlapping, but we are able to separate those.
Great. How long does it take to calibrate, and what is the maximum concentration to calibrate? Minimum, sorry, I've read it incorrectly, sorry. So what is the minimum detectable limit?
Concentration to, I mean, yeah, we are dealing with very low concentration, so nanogram is nanogram.
Or probably what's the minimum detection limit?
Yeah, I know. I was thinking, yeah, minimal detection is nanogram, but if you want to calibrate the monitor, how much silica containing dust or mineral, you need to send it to us. About 4 ounces.
The Nanozen captures a sample onto a 25mm filter for lab analysis. How does this lab result compare to sample collected with traditional size selective sampling?
So the cassette, the Nanozen internal cassette, Nanozen internal cassette has some particle loss. Most people wanted to compare to the pump and filter method, so we actually have been doing side-by-side tests. One side is our monitor, the other side is the cyclone, and actually because in the field it's not well mixed particles, unlike our wind tunnel, you can generate a lot of particle and mix it well. So however method you do side-by-side test, you give you approximate comparable result. But in the field, when large particles settle very quickly, small particles will sustain in the air for a long period of time. It's not that easy to do side-by-side, but we have done enough side-by-side. There's what we call manifold need to be installed on top of pump and filter and the monitor to be able to collect a proper side-by-side. And that's we have a lot of success doing that properly. The internal cassette itself, we are still improving because there is some particle loss depending on the humidity. There is some particle loss that we have noticed. So if you have done some studies and wanted to have a dialogue and chat more, we could do that because we've done some studies in-house. I'm curious to see the size study of just the cassette, internal cassette.
Thanks, Winnie. So what's the difference between 3-litre normal gravimetric sampling pumps and 1 litre per minute for Nanozen?
The pump, well, depending on what kind of silicone, what kind of cyclone you are using for silica 1, 2, yeah. So the dust count itself is 1 liters per minute. Our new SAS right now is only running 0.5 liters per minute. Cyclone, depending on which cyclone you use, is 1.7 or 2.5 liters per minute.
So here's one for you, Winnie. Is there a safe level of silica in Winnie's opinion? What do you think?
Probably not, unfortunately. Yeah, no, probably not, unfortunately.
Okay, thanks. We've got a few more here. Can you clarify these are personal monitors? If so, how susceptible are the electronics, light sources, mirrors, etc., to rough and tumble of real-world personal use in tough environments?
Well,
They're
Very
bent up.
robust.
Yeah, the internals are CNC machined aluminum, CNC machined impact resistant and fire resistant plastic. And they've been dropped, dumped, driven over, and I won't say they don't suffer damage, but they'll still work in most cases. So.
Yeah, don't tell any of the workers.
Yeah, that's right.
These are robust. Well, even I have. Well, I think I dropped the monitors a couple of times.
They don't have to be kept upright, and they don't have to. There's no orientation they have to be in. They are water resistant, like an IP62 or IP60, but they're not IP65. You can't immerse them in water, but they're pretty robust.
Thanks. Is the method for the use of the machine, the Nanozen, the DustCount, being accredited for use in legislated workplaces, so mines, quarries, etc.?
So it's definitely not yet. We are trying to change the status quo by working with the industry association first.
So OSHA says yes, but it has to be calibrated to a.
No, but not the regulatory approved method.
Yeah. Not for legal.
Yeah. It is still an alternative method for now. We are trying to push the regulation changes. We are.
So I think it's the state of Western Australia allows you to put your data onto the regulatory website as a backup or a reinforcement of the legal test.
Okay, got a few more questions here. Is there capability for this monitor to expand to other contaminants such as arsenic?
Arsenic. So this spectral aerosol sensor has been used for other chemicals now. Arsenic, not yet. So metal oxide, metal sulfide, chemicals, drugs, many different type of chemical aerosols. Yes, it has been applied to those. Arsenic, not yet. Oh, I'm so hesitant to say yes.
One of the issues, of course, is once you use it, it's contaminated. So then you need to properly clean it. So we do have a facility in Vancouver, a glove box that we can actually take things apart and clean them.
Yeah.
But it's not an easy thing to do.
Yeah.
So
probably AirMed will adopt that as well, right? So
Okay, I've got a few more here, Winnie. You mentioned you can calibrate the unit to specific mineral particulates. How many calibrations can you have at the same time, and can you monitor different minerals simultaneously?
so the SAS is designed to measure three buckets. Yeah, three.
plus the background.
Right. Three plus, yeah, but the 3 plus everything else. So you can then specific calibrate to determine 3 chemicals of your choice, and we dump everything else that didn't calibrate into one bucket. It's called other.
No, and then
So
there
3,
would have to be a calibration for each of those 3 done by us.
Yeah. Or in
Okay.
Melbourne, I guess,
It's a
right?
one-time calibration. It's not something you have to do constantly.
Yeah. So in Melbourne, I guess, yeah. One site in Canada, one I guess one in Australia, right? Not 2, 1.
Okay, a follow-up to an earlier question. How sensitive is the DustCount given the reduction in exposure standards and increased runtime required for traditional gravimetric methods to meet the lower proposed limits?
Yeah, so both the DustCount and SAS are being used for 0.1 microgram. So that's yeah. So 100 nanogram per meter cube is what the sensitivity now.
Okay. Does the Nanozen require a software package to upload and retain data?
No, so there is a software, but there is a software, but you download everything in, so everything will be saved in the monitor, or you can download into an Excel file, or there is a software.
Yeah, 3 different options.
Yeah, different options.
It always stores the data in the device. Then you can either at the end of the test or during the test, you can pass the data to a software package that we have that will graph it for you or send it to an Excel file. Or it can also automatically send it to a location in a computer file that can be constantly read by an automated system.
Yeah.
Okay, here's a few more still. Please adapt the sensor to asbestos and monitor different asbestiform minerals simultaneously. I think that would be possible, Winnie.
Yeah, I've been asked about asbestos as well, because in Canada as well. So it's funny enough, we have a project with the asbestos-like polymer material that somehow would be before asbestos, but yeah, definitely. I'm trying to push arsenic to later, but asbestos, both Australia and in Canada, are priority. So we are talking to partners about how we can get that started.
Great.
We have a patent on a sensor that we believe could be used to detect asbestos, but it's just not high on our list right now.
Yeah, but we are starting with a asbestos-like polymer in the spring. So that will give us a lot of information on how our monitor can be modified to also detect different type of asbestos.
Okay. Do you know when it might be approved by the regulator, i.e. DMIRS in Western Australia? Oh, here Melicia's going to answer.
Can I answer that, Winnie?
Yes, please.
So sorry, Peter, do you want to repeat the question? Regulators in Western Australia?
Yeah, do you know when it might be approved by regulators in, for example, Western Australia?
Look, I think the way that industry is going and the regulators, I think even working with NIOS and others, the sort of industries is now thinking that should we need to be like to adopt 40 years old traditional way of measurement, or we should be considering more real-time monitoring to actually have a quick response for our workers. So regulators have recognized the real-time monitoring, and they are actually advising industry that if they can sort of adopt that one as quick as possible. There is not a firm timeline has been given to us so far, but the need and the urgency, and then actually putting the controls on once actually the real time will detect any situation, it is a greater benefit that they are actually explaining to the industry quite a lot. So I think Peter Briscoe mentioned previously what they are actually helping industries, that they actually have started creating additional data entry into the database, that if any sort of resource industries would like to adopt the real-time monitoring, they can actually report some of their data into that format as well. Again, it is not reflecting the normal traditional method, but it's just additional options available for industries to work towards that point. Hope that explains.
Yeah. Thanks, Malish. We've also got another question about Australian-based intrinsic safe certification, ANZEX, and I know there has been some discussions about it, Greg, so I know is some progress being made in that region. Malish might be able to answer that as well.
Yeah, it's basically ICEEX, which is the like the same underpinning certification. So we have already that one. So discussions are in progress with the approved lab in Australia, and the procedure has been started. So it's just a matter of timing that when we can actually have that sort of paper studies done with them to actually get the certification very soon. The short answer is now.
Thanks, Malesh. So that looks to be about all the questions so far. Or someone's asking about how much it is. So it's a bit over $10,000 at the moment. I guess we might wrap it up there. Thanks everyone for coming along, and I'm sure that you found the session both enlightening and insightful. If you've got any other questions regarding Nanozen products, please don't hesitate to reach out to your local AirMet representative. AirMet, as Winnie's mentioned, is the exclusive distributor for Nanozen product line in Australia, and we also operate a factory accredited calibration facility in Melbourne. And you're also welcome, I'm sure some of you coming to the AIOH conference in a few weeks, where we'll have Nanozen DustCount on display. Winnie and Peter from Nanozen will also be there and can discuss further if you're interested in the spectral aerosol sensor that they're developing, which it looks very promising for identifying silica. And finally, thanks Winnie for your time today. And we really appreciate you accommodating our time difference as well by presenting in the evening. So thank you, everyone. Thank you, Winnie.
Yeah, thank you very
Thank
much.
you.